All right. Well, thanks very much for the opportunity to come and talk. That is indeed what I'll be talking about. I always like to start these things with a bit of an outline for where I'm going, sort of a very general outline without many details. Basically, I'm going to start with some motivation and some background, and I'll talk about what, in particular, what the main object I'll be thinking about in this talk, Vasosoro blocks. I'll talk about what those are in 2D, so I'll just remind you their definition and some of the things that we've learned for them. And this is all basically going to be motivation. And then I'll move on to the point of the talk, which is sort of the strategy we're going to apply. And in particular, I'll talk a bit about the holographic setup for the actual calculation we do. And the goal of this talk is going to be basically to try and generalize Vasosoro blocks in 2D to higher dimensions. All right? And I'll talk about some of the obstacles to doing that, conceptually and practically. And then I'll talk about how we can try and overcome those obstacles. And then finally, I'll talk a bit about some of the details of the methods, and depending on how much time I have, I'll talk about some of the results that we get. All right, so that's basically what we're going to do. So the goal is see if we can generalize the concept of Vasosoro blocks that work in 2 dimensions to higher dimensions. All right, and let me start just by reminding you what Vasosoro blocks are. Vasosoro conformal blocks. So in 2D CFTs, they're basically contributions to the operator product expansion from an entire irreducible representation of the conformal algebra. And there's one in particular that's most important for what I'm going to be saying, which is the vacuum block. And this is the irrep that contains the vacuum in it, or in terms of operators, contains the identity operator. So if I look at the operator product of an operator with itself, that guy always contains the identity operator. But the conformal symmetry relates its contribution to an infinite number of additional operators, namely the stress tensor and what you can think of as stress tensor squared, stress tensor cubed, and arbitrary higher powers. All right? And all of these guys are always there in the OPE of an operator with itself. And in particular, their contributions are controlled by the symmetry of the theory, so we can calculate them. So here I've used Vasosoro block for the term in the OPE. We often use the same word for the contribution of that piece of the OPE, its contribution in a 4-point function. All right? So we can just apply the same OPE twice. So I have 2 pairs of operators of the same operator. And substituting this in, you get a contribution, again, from the identity operator. You get the contribution from a single stress tensor times, these are the OP coefficients for that guy. And here, instead of writing T, I'm going to write the conformal block for a single stress tensor. And the important point is this is a known function, right? You can write it down in closed form in terms of hypergeometric functions. And then not only a single stress tensor, but you also get the contribution from T squared, which again, this is some calculable function, and so on. And the resummation of all of these guys is what we call the Vasosoro vacuum block. All right? And what's important about it is, as I said, it's always present in a 4-point function of this form. And furthermore, it's controlled by Vasosoro symmetry. So if we're willing to work hard enough, we can compute its contribution. Now, that in itself makes it interesting, but it maybe wouldn't be so interesting for trying to understand quantum gravity. just the fact that it can be calculated. But it turns out that this contribution knows a lot about ADS3 gravity. All right, and the reason for that is relatively easy to understand. So, just a general fact about ADS CFT is products of the stress tensor are dual to multi-graviton states. So this resummation basically knows about the nonlinear resummation of multi-gravitons in GR, which is another way of saying it knows about GR. All right, so this is why this is a particularly interesting piece to compute, because if we can compute it, we can actually, in this case, CFT2's, the algebra actually knows about GR and ADS3. All right, so let me just back up a bit and make some general comments about strategy of approaching quantum gravity. And I'll make this comment in the form of a story. So some of my best friends are phenomenologists. And there's one who works down the hall from me who I'm very good friends with. And every now and then we're at lunch. And he tells me working at quantum gravity is just a huge waste of time because we have no experiments. So all we can do is study toy models. And without experiments, we'll never be able to convince him that these toy models have anything to do with the real world. And then we yell at each other for a while, and we get mad, and then we apologize, and then we kiss and we make up. So the moral of the story. Well,
the experiments are working out so great for them anyway.
So the moral of this fable is that I really need to get better friends. No, that's not true. He's a very good friend. No, the moral of this fable is really just a comment about different approaches to quantum gravity, and these two types of strategies have sort of relative advantages and disadvantages. So one strategy for approaching physics that we don't understand that has been very fruitful historically has been study toy models. And in that case, you try and solve the toy model, and if you've chosen it well, you can solve it. And then you have to argue that the toy model contains is somehow representative of the real world. Sort of the contrasting point of view, contrasting strategy for universal pieces is we can try and compute things that are in any model, sort of model-independent universal pieces that are always there, and you can try and compute those. And if you succeed in computing those, you then have to make a different type of argument, which is that somehow those capture the relevant physics, the physics that you're actually interested in. And so for the Virasoro conformal block at large central charge, it turns out that it actually knows a lot of the physics of gravity that we're interested in. So let me just mention some of it. From studying large central charge, the 2D Virasoro block, it actually knows about black hole thermodynamics in ADS3 and the corresponding information loss. It knows about the saturation of the chaos bound on the Lyapunov exponent. It knows about the Ryu-Takanagi formula. And perhaps most interestingly, it knows about some violations of unitarity that occur in perturbation theory and non-perturbative effects that resolve some of them. So that's all motivation. Now what we're going to try and do, largely motivated by this story, is to try and generalize Virasoro vacuum blocks to higher dimensions and see if we can reproduce some of the success there. All right. So how are we going to do that? So this brings me to the second part, which is what is our strategy and how are we going to use holography as part of that strategy. And let me start by mentioning right away, you might say, well, obviously this is going to fail. There are just a bunch of obstacles in D greater than 2. And the first thing you have to do, since you don't have Vasosoro algebra, is you have to decide what should you even mean by the Vasosoro vacuum block in higher dimensions. And I wrote this here in such a way to sort of motivate what I think is the most natural generalization to higher dimensions, which is basically to do exactly the same thing in higher dimensions, that is to resum t to the n operators in the CFT. All right, so we want to resum all of their contributions, not just t, but t squared, t cubed, etc., to a 4-point function of this form. All right, so it's not quite so simple because we have to ask what that even means. That is, what do we mean when we say something like t squared? And the reason that's ambiguous is when you try and define this operator, you have two products of the stress tensor at different points. You bring them together. That operator product has singularities, and you have to decide how you're going to subtract them out to define this composite operator. All right. So the way I'm going to deal with that is that's not really so hard. I'm going to just take the infinite central charge limit, and this entire talk is going to be from now on about the infinite central charge limit. And in that case, all correlation functions of the CF of stress tensors among themselves can be described by a generalized free field theory, and so there's a canonical definition. All right. All right.
Liam, I'm just slightly confused about where generalization came on here. Are you talking about more than the Vasosoro block, the vacuum block, or not?
It's d greater than 2.
Oh, that's the generalization.
Yes.
Okay, sorry. Okay.
So we don't even, yeah. Vasosoro is d equals 2. So I guess recently the way to deal with quantum gravity is you're supposed to go down in d, so we're going the wrong direction. Sorry. All right, good. So we have a canonical definition of what t to the n means, but we have a more serious problem, which is we have to figure out how they contribute. How do t to the n operators contribute? And we're going to be looking at 4-point functions of this form, where I've replaced a and b with L and H. And the reason is the light operators, L stands for light, which means their dimension is order 1 at large central charge, and H stands for heavy, which means that their dimension is order the central charge. And so what I mean by how do the t and operators contribute in precise words, what I mean is what are their OP coefficients? All right, so in 2 dimensions, their OP coefficients were all controlled by Vasosoro symmetry, and we knew that we could calculate them. Here, we don't not only do we not know how we would calculate them, we don't even know how constrained are they? Are they constrained by anything? Are they so unconstrained that if you think of sort of scanning the space of CFTs, you could dial all of their OP coefficients completely independently? All right, so that would be a problem. All right, so in order to resum them, we have to have some sense of what we're resumming. And the way we're going to try and get some information about how constrained or unconstrained they are is we're going to use ADS. Basically, I want to think of it as a lab to look for a universal behavior.
Can I ask one other thing?
Yep.
So in 2 dimensions, C is an analytic parameter that appears in the conformal block, and I can think about this limit.
Yep.
In in higher dimensions, I guess you have to imagine you have some actual sequence of theories or something.
Well, yeah, so if you have an algebra, you can think of it as just a parameter in the algebra. If you have, or we're going to be doing everything holographically, so it's Newton's constant, so we can dial Newton's constant.
Yeah. But you just, CT is the 2-point function of the stress tensor?
CT is the 2-point function of the stress tensor, that's right. And yeah, that's right. Good. All right, so so the way I want to use ADS as a lab is basically, a large part of what's behind ADS CFT, and I think a pretty significant amount of the work on ADS CFT uses ADS sort of as a machine for generating CFTs. Right? That's one way of thinking about what a large part of ADS CFT is. You can write down Lagrangians in ADS, and those will give you correlation functions for CFTs at the boundary. And so you can just think of this as a way of sweeping through spaces of CFT data very efficiently by writing down large classes of Lagrangians in ADS and dialing the parameters to get a sense of what's allowed. And there's a very tight connection of this approach to effective Lagrangians in particle physics, something like the chiral Lagrangian. If no one had ever told you about current algebras, or more realistically, if you had heard about them but just didn't want to learn about them, what you could do instead is write down effective Lagrangians. As long as you write down the most general thing allowed by symmetry and other constraints, then you can learn about, say, pion scattering. And it's a more intuitive sort of way of looking at it. So basically, we want to take a similar approach here. Now, if I really applied the strategy I just described, what we would do is we would write down the most general Lagrangian allowed in ADS. Arbitrary numbers of fields, arbitrary numbers of gauge fields, arbitrary higher curvature terms. Basically, we would just be extremely general. And we're not going to do that because that's too hard. Instead, we're going to make some simplifying assumptions. So I'll describe the class of theories that we're going to look at. And then if I have time at the end, maybe I'll discuss ways in which this can be generalized. But let me just start with a simple class where we can do calculations. So I'm going to assume we have an effective Lagrangian for the metric and a single scalar field. And in the bulk ADS Lagrangian, I'm going to allow not just the Einstein-Hilbert term, but arbitrary higher curvature terms with arbitrary coefficients. Almost wrote the field of real numbers there, which is not what I want. And then we also have minimally coupled scalar field. All right. So if you want, you can think of it as if we had a bunch of other heavy fields and we integrated them all out and they generated all these higher curvature terms. Okay? All right. Now, what we're going to do is to understand what the contributions from TDN operators can look like is we're going to compute, the way we're going to compute a 4-point function like this is we're going to compute something, we're compute it in the following way. We're going to look at the 2-point function of the light operator associated with phi in the background of the black hole corresponding to solutions of the corresponding field equations. And the point is, you can think of the black hole operator, the black hole, as the background created by the heavy operator in this 4-point function. All right? Once we've computed this 2-point function in the black hole background, then we can extract what these OP coefficients are for TDN operators, basically just by doing a conformal block decomposition. All right? And what we'll find is we have, just by looking at their dimension and spin in the conformal block decomposition, we can read off the contribution from the TDN operators. I'm going to call this combination of these two things p t to the n. And then there are other operators which are not multigravitons, which are what I'll call the double trace operators, double trace of O light, O light. So let me just write them schematically as C light, light, O light squared, C heavy, heavy, O light squared, and then their corresponding blocks. All right?
What about O heavy square?
So it's not going to show up, right? We're doing a conformal block decomposition, so we look at it order by order in the lowest few powers, and so it, at infinite delta H, it never shows up. All right.
OL, the O light square is a new operator with double.
O light squared is the product. Yeah, it's just O light. It's just the product of this guy. And then there are an infinite number of those which you can make by putting derivatives on one or the other of the O lights in such a way that you make a primary operator.
But why didn't you also include H heavy square?
So that was what Daliang's question was. The reason is that they have dimensions which are infinite in the infinite central charge limit, and so they don't show up at any finite order in the conformal block decomposition.
Oh,
All right. So I'll describe a little bit about how we do this computation, but before I do that, let me just tell you the punchline, which was in the title, but I can now say it more precisely. So the punchline is that the OPE coefficients for the lowest twist t to the n's are universal in the following sense. They depend only on the dimension of the light operator and the following combination, which I'll call F0, which is delta heavy divided by the central charge. This is, just to remind you, this is at Ct goes to infinity. Okay? So let me write that in equations. So for the lowest twist t to the n's, this OP coefficient, this product of OP coefficients, p t to the n, is equal to f0 to the n times some function, depends on how many what n there is in t to the n, but that's all it depends on, n and some function of delta light.
So the other thing it could have depended on was the coefficient of this R squared.
It could have depended on all those coefficients.
Yeah.
Exactly. That's right. And for the subleading twist, they do. They do depend on them. Okay. All right. And let me just be more clear about what t to the n. So for n equals 1, there's obviously only one, the stress tensor. For n equals 2, there are three different guys. There's t mu nu, t rho sigma. There's t mu alpha, t alpha nu, and there's t alpha beta, t alpha beta. So the spin of this guy is 4. Of this guy it's 2, and this guy it's 0. And so the twist, which is the dimension minus the spin, in this case is equal to 2d minus 4, because the dimension of the stress tensor is d. In this case it's 2d minus 2, and in this case it's 2d. So this is the lowest twist. All right, and so you can easily see the lowest twist is just the guy who you don't contract any of the indices. All right, and the minimum twist, I mean, is easy seen as counting for any number of t's. The contribution to the dimension is going to be n times d, and the contribution from the spin is going to be minus 2 times n. So at any number of stress tensors, the lowest twist is t min is equal to n times d minus 2. All right?
You don't have to like subtract out pieces of that, like involving contractions with the matrix or whatever?
Subtract out pieces of what?
Well, for example, that first one you wrote, if I contract it with g mu nu once or twice, I can get the other ones, right?
Well, so this all sort of taken into account automatically when you do this decomposition, because this depends on the dimension and the spin. And once you know the dimension of the spin, the conformal block is just a known function. So we're defining this operator as primary operators with, I've separated them cleanly into primary operators with dimension delta equals 2 times d.
It transforms in a reducible representation of the rotation.
I think he has subtracted off all that.
Sorry. You're asking about, yeah, I'm being schematically.
You mean that
Yeah.
minus-
That's right.
okay.
That's right. All right. So why? Okay. So good. So the lowest twist guys are universal, and what's nice about lowest twist is low twist things tend to dominate when you go close to the light cone. So we can actually take a light cone limit where these guys are the entire answer. All right, so let me describe what that limit is. Okay, good. So we're going to take a light cone limit. And in terms of, so in the bootstrap, we like to use these ZZ bar variables, which are just ways of writing the conformal invariant cross ratio. You can use them in any dimension. So one way to get to the light cone limit is to take Z bar goes to 0. And in this limit, the global blocks take the following form as a function of twist and spin. This is a result first worked out by Dolan and Osborne, I think. They look like ZZ bar to the tau over 2. Tau is twist. Z to the L. And then there's some hypergeometric function, and you don't really care about it. But the important point is that we want to look at the Z bar dependence here. And I told you that the minimum twist is given right there. It's n times d minus 2. So at small z bar, this shuts down like z bar to the n times d minus 2 over 2. OK? And anything with higher twist is suppressed by more powers of z bar. All right. So if that were the end of the story, it would say that yes, they dominate, but they're all being suppressed by small z bar anyway, so they don't. So don't they all just contribute nothing? And the way we compensate for that is we make the following observation about the OP coefficients, which is that for n stress tensors, they're proportional to f0 to the n. And so these guys always show up in the conformal block decomposition in the following combination: f0, z bar to the d minus 2 over 2 to the n. And so what we actually want to take is the limit z bar goes to 0 with this combination fixed. All right? Let me just tell you, physically, this is basically a high temperature limit. All right, so the reason for that is pretty intuitive in ADS. This is basically g Newton times the mass of the heavy operator in ADS. All right, so in the limit where the mass becomes very large in ADS, the temperature becomes very large. Okay. So if we take the high temperature and the near light cone limit, then, and what by that I mean this fixed as z bar goes to 0 and f0 goes to infinity, then these lowest twist guys are the ones that that dominate. All right. Good. All right. So that's basically the punchline. Is that this is, at least in the class of ADS Lagrangians I described, this is universal. You can compute their coefficients, and they dominate the 4-point function in this high temperature near light cone limit.
So did you show yet why it doesn't depend on the R squared? And
I did not show that. No, I just stated it. But I will say a little bit more about how you see that. How you see that's true. All right. So far, so good. All right. Good. Okay. Now let me discuss how we actually see that. And the idea is we're looking at the 2-point function in the background created by this heavy operator. Right, this is a primary scalar operator. So the background metric should be stationary, should be spherically symmetric, and should be asymptotically ADS. And so that leads us to write down the following metric. And I should mention, I'm actually, for simplicity, I'm going to be considering the limit of planar black holes, basically because calculations are easier there. Though from all the calculations we've done so far, it seems like this universality is true generally, but strictly speaking, we've only proven it in the planar black hole case. All right, so good. So we're looking at this background metric, and we take these functions to be asymptotically ADS, so they look like this. And then there are higher order corrections. Right, so you should think of things like f2 over r to the d plus 2 plus dot, 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 f4, etc. And similarly for h of r. All right. And different Lagrangians for the metric, different higher curvature terms, will basically just affect this in terms of different f of r and different h of r. Okay? So in fact, when we started thinking about this, we were only looking at a specific class of higher curvature terms called quasi-topological gravity. And basically what's special about those theories is in those theories, f of r and h of r end up being the same. More generally, they won't be. But this gives us an efficient way of basically of organizing the effects of higher curvature terms. And all we have to do now to compute the boundary 2-point function, so just to remind you, we're computing this thing, the boundary 2-point function in the black hole background. So to do that, first we solve for the bulk to boundary propagator phi equals 0, okay, where this depends on the background metric. And we do this order by order in a 1 over r expansion. Okay? Yes?
Is it possible that when you turn on higher derivative deformation, the definition for the energy also changes such that your higher order term will appear in your energy?
Yeah, well, so good. So the point is, this depends in a complicated way on the coefficients of the higher curvature terms, right? But because when we do the conformal block decomposition, the coefficient of a single stress tensor, the coefficient of a single stress tensor is just f0 times delta light over, f0 times delta light. And the Ward identity fixes that in terms of delta h over ct. All right. So even though the physical quantities delta L, delta H, and Ct might depend in a complicated way on the parameters of the Lagrangian, the point is once you re-express the OP coefficients in terms of the physical charges, they're universal, right? So, all All right, so and that's how you should do it, right? You should write, if you write physical things in terms of other physical things, that's how you see the universality, right? All right, good. So so the point is, the hard work is solving this thing. That's not so easy, but once you've done that, then it's straightforward to extract this guy. Extracting that once you have the bulk to boundary propagator is trivial, because O light is just equal to the limit as r goes to the boundary of the bulk to boundary propagator.
Sorry, just very naively, Liam.
Yeah.
You can't just solve the equation in a 1/r expansion, right? Because you have to impose something in the steep inside, right?
Good. I'll come to that in a second. Yes. Very good question. All right. So the punchline is that ends up only affecting the double trace operator OP coefficients. It doesn't end up affecting the stress tensor OP coefficients. I'll say that again in a minute. All right. Good. All right. So this is the idea. Once you've computed this, you just extract the 2-point function, and then you do the conformal Leck decomposition. And so what you have from that is, if you just look at the lowest twist pieces, which are universal, you get the lowest, what you can think of as a lowest twist block, which I'll call VD, and I'll write it as a function of two variables, which are just a way of rewriting Z and Z bar. So we get it's a sum, n equals 0 to infinity, an times something like this. And these can be, so the point is we compute these. And this is boundary time. And sigma is basically parameterizes the angle from the light cone. All right, so you think of it like this. Looking very close to a light cone. So t is moving along the light cone, and sigma parameterizes the angle. From this you get efficient recursion relations, which let you compute these to very high order. And for some magic values of delta light, these can be all computed in closed form and be resummed into a closed form expression. All right. So let me just mention. Let me come over here. Let me just mention some points. First, I'll make a comment about what goes into solving this, and then I'll make a comment about boundary conditions. All right. So first of all, solving the bulk equation of motion for the bulk to boundary propagator is simplified by choosing nice variables. And once you choose the right variables, it's possible to just take a limit where the equation of motion for phi, and the equation of motion, remember, is just box minus m squared phi equals 0. It keeps only the lowest twist stress tensors. And second, it manifestly depends only on F0. It doesn't depend on F2, F4, etc. Okay? So that's basically how you see that it's the equation of motion only depends on the equation of motion is universal. And the second point is for the t to the n contributions. You don't need an interior boundary condition. All right, so this was sort of a surprise to us. And that should be contrasted with the double trace contributions. Double trace ops, and these are these operators O light squared, O light, d, etc. Where these guys do depend on the interior boundary condition.
Interior boundary domain horizon.
Yes, that's what I mean. All right. So I think this is physically interesting because what it says in sort of more physical language is that the double trace operators, or the double trace OP coefficients, are what encode the difference between a black hole in the bulk versus if we just acted with a local bulk field with a large dimension. All right? So imagine if instead of computing it the way that I computed it, imagine I had an extra bulk field, phi heavy, and I just inserted it in the bulk, and that's going to have some background versus the black hole, which has far away from these guys, they look indistinguishable, but as you come very close to them, they look very different. Particularly, the black hole has a horizon and a singularity inside, whereas phi is just smoothed out over its constant wavelength, and so the boundary condition for it is very different. And in the language of thermodynamics, if we compute a black hole background, really what we're doing is we're computing a canonical ensemble, whereas here, with just a single phi, it's actually a microstate. Right? It's just the state in the bulk with a single phi particle. And so somehow the double trace operators are actually, their OP coefficients are what distinguish the background in the canonical ensemble versus microcanonical ensemble. All right?
You mean actually we can using these channels to see whether the heavy operator produces a black hole or not?
You would look at the double trace OP coefficients, right? But the multi-stress tensors don't know.
But
Okay.
the stress tensor correlator knows, right? Because you can.
No. The stress tensor. So this was known for a million years. The stress tensor is just the conformal block associated with the single stress tensor that just doesn't care.
But if I
right?
look at the 2-point function of the stress tensor.
No. That's so good. So what I'm actually talking about, right, is O light, O heavy. I'm talking about the sum over conformal blocks. So that's what I mean. And for a single stress tensor, this OP coefficient is fixed by the word identity, so it can't possibly care.
Yeah.
All right. And that, so let me say actually an intuitive way of thinking about that, which might give some intuition for why it's true for the higher guys as well. So this is some work by I think Snively, Krauss, and Perlmutter. So what they, if you wanted to actually compute this for say a single bulk operator, what you would compute is a Witten diagram where you have O light, O heavy, and let's talk about just the contribution from a single stress tensor. You would compute a Witten diagram where you use this bulk boundary propagator, and then you have a single graviton exchange. What that would give you is the contribution from stress tensor and double trace contributions. What Krauss, Snively, and Perlmutter showed was you can do something, you can make a slight modification to this, where instead of integrating this interaction point over all of the bulk, which is what you do in usual Witten diagrams, you can integrate them along a geodesic. And what that does for you is it picks up just the contribution from the stress tensor conformal block. Okay? So instead of integrating the interaction point for all space, you just integrate it along this geodesic. Right? So this is a geodesic. And there it's kind of obvious that it's not going to care what's going on at the horizon, because we're doing a short distance expansion of O light to light. In a short distance expansion, this geodesic just doesn't approach the black hole horizon. And now I think it's very natural. So the way we found that they don't depend on the horizon boundary conditions is just by imposing the boundary conditions, seeing what happened. But I think a very natural heuristic reason is probably if you were to do the same thing for multiple gravitons, you would, integrating along just a geodesic, would probably pick out the multi-graviton stress tensors.
What about the single trace operator, which is different from stress tensor?
What single trace operator?
Say assuming you have some scalar, in the gravitating.
Oh, like-
The field would be a single trace operator.
Yeah, let me talk about that a little bit. I think I've said basically good. So I basically said what I want to say. So let me address that point. So this was. Let me come back to the setup. You're asking, what if we go ahead and put in more fields in the bulk? All right. Remember, I'm not working with the most general possible Lagrangian. First of all, I'm assuming all I have is phi and g mu nu. So you're asking, what if I added something like lambda phi squared chi, right? That's basically what your question is. Now, what I've basically done is I've said, what I've actually done is I said, let's just set that to 0. But the way I want you to think about it is what I've done is I've said, imagine that you have a CFT where you have something like n equals 4 supermills, where you have a parameter that you can dial to make all these guys heavy. All right, and then order by order in 1 over that parameter, you can integrate them out and absorb them into the higher curvature terms. Okay, so to all orders in 1 over the mass of this guy, this universality should hold. Okay. You're shaking your head, which means you disagree, but maybe we can talk about it afterwards.
My question is that it seems here you assume that in the configuration that in this configuration you assume that your scalar field vanish. Like
No.
mathematical
No?
scalar field
Sorry, in what sense have I assumed that it's vanishing?
in the configuration.
I mean, I think, okay, so I mean, I guess the thing that I just wanted to talk about a little bit is, so far I did this computation in this special class of Lagrangians. Of course, what I want to say is that it's as general as possible. And so that's why I'm saying, how much can we hope this simple Lagrangian can generalize to a larger class of theories? Okay, and the first comment I want to make is that if you have extra light fields, you definitely should include them, right? I think that will change the answer if you have additional light fields. However, if you have additional fields with a mass parameter that you can dial to be large, I'm saying to all orders in 1 over that mass, you can just absorb them into the relevant interactions. Okay. So what you would want to do if you wanted to connect to something like n equals 4 superannuals, you would want to include all the protected fields in the bulk, and you would want to redo this calculation and see how they affect the OP coefficients. And then that would be sort of, you would get a different universality statement, which should actually be satisfied in the OP coefficients for multi-stress tensor operators at large central charge in n equals 4 superannuals. So let me just finish by basically one of my comments about the future was exactly this point. I think it'd be interesting to add extra light fields in bulk and see how much they matter. And then you should be able to connect and just check whether it's true in n equals 4 supermills at large Tift coupling. And so far, this has all been a derivation on the gravity side. Of course, it'd be cool if there was a way to get this from thinking about if there was some algebraic way of deriving this. Maybe at large central charge and large temperature, maybe there's a symmetry that emerges with an algebra associated with it. All right. Thank you very much.
We have time for a couple questions.
You said you had a recursion relation for these lowest twist products.
Yeah.
So in 2D, these recursion relations are derived by considering the null state structure of the Vasosoro algebra.
Yeah.
Is there anything like that?
Yeah, so that's a very interesting question. So I said you can resum these for magic values of delta light. The magic values are delta light equals -1, -2, minus integers up to some. Those are exactly the guys who, under the global conformal algebra, have null descendants. And in fact, the way you can get the Vasosoro blocks in 2 dimensions is by taking the degenerate operators and taking the large central charge limit. And in that case, again, those degenerate operators, they have to, I mean, their dimensions agree with exactly the dimensions just from thinking about the global conformal group. So you get, for these guys, you do get equations, degenerate equations for the 4-point function associated with the global conformal group. And maybe you could understand these contributions that way. Rich?
Well, yeah. Sorry, since there's a lot of this multi-graviton exchange
Yes.
has some deja vu from the Eikable sum. Are
Yes.
there special cases in which this exponentiates?
I think so. Yeah, I think so. I mean, I think the connection with the Icona limit is interesting, but it's a little more involved. Let me talk to you a bit about afterwards.
Algebraically, is there
Yeah.
a case in which this exponentiates? Is there a special example?
Well, I can tell you one thing, which is in 2 dimensions. If you take, there are some cases where it expansions. Let me leave it at that.
If I can follow up, in the sum, each turn a large
Yeah.
t diverges. So can you say something?
Sorry, what?
in the
Oh,
sum? Yeah. So can you say?
you mean because it's a power of t?
Yes.
Yeah.
If you treat this icon,
Yes.
this way, it's 10.
The sum has finite radius of convergence.
Does it diverge at t equal to infinity?
It diverges before you get to t equals infinity. There's a finite radius of
finite
convergence.
radius,
Yeah.
okay.
But we can calculate the radius of convergence and the behavior at the radius of convergence.
You can resum it.
Well, we can figure out what the power law divergence is at the edge of the radius of convergence.